It's about to happen again.
It's the first word from space before history is made. From landing a man on the moon to assembling the International Space Station, NASA's Johnson Space Center serves as the iconic beginning to some of the greatest moments in American history. Moments that are triumphs of engineering and international cooperation. Today, we are
landing a man on the moon and returning him safely to the Earth.
Tranquility Base here. The Eagle has landed.
Good afternoon and welcome to NASA's Johnson Space Center. I'm Chelsea Bayarte here live in Mission Control Houston. We're on flight day 10 of NASA's Artemis I mission, and today the Orion spacecraft will conduct a translational burn to insert the spacecraft into a distant retrograde orbit, or DRO. This is a relatively quick burn expected to fire for 1 minute 28 seconds beginning at 3:52 and 28 seconds p.m. Central Time, 4:52 p.m. and 28 seconds Eastern. Distant retrograde orbit is highly elliptical, oval-shaped orbit around the moon. This orbit is unique to Artemis I and will not be used for Artemis II, Artemis III, and beyond. It's highly stable, so little fuel is required to stay there, as we use this Artemis I mission to put Orion's systems to the test. And here to talk about future orbits in just a little bit is NASA's Deb Ludman. She'll be joining us as a guest shortly on in our coverage later today. We'll also be joined by NASA's Dan Hewitt back at the moon board to explain a little bit more about what distant retrograde orbit is. We're here live in Mission Control's White Flight Control Room with NASA Flight Director Rick LeBrode at the helm, overseeing a team of flight controllers who are getting ready for the distant retrograde orbit insertion burn. This is the same building as the International Space Station's Flight Control Room, but it's a separate room dedicated to overseeing Artemis missions. This is a live view that you're getting on your screen now. So let's talk a little bit more about how we got to this point. The spacecraft launched on a Space Launch System rocket on November 16th, and by its third day, it was halfway to the moon. On November 21st, Orion performed an outbound powered flyby burn, the first of 2 maneuvers required to enter DRO, the second being today's orbital insertion burn. At the time of outbound powered flyby, Orion was just 81 miles above the lunar surface. And throughout the mission, the spacecraft performed a series of outbound trajectory correction burns to put Orion into the lunar surface, into the proper configuration to enter distant retrograde orbit. So remember the number that I just told you, 81 miles above the lunar surface on November 21st, and by November 22nd, Orion exited the gravitational sphere of influence on the moon and was at a lunar altitude of nearly 40,000 miles. It's going to continue to get farther, and shortly after today's distant retrograde orbit insertion burn, Orion will reach its maximum distance from the moon at 57,287.76 statute miles. Tomorrow, November 26th, Orion will pass the distance record for the human-rated spacecraft originally set by Apollo 13. That record is 248,655 miles away from the Earth. Orion is expected to break that record at 7:40 a.m. Central, 8:40 a.m. Eastern tomorrow. If you want to hear a little bit more about that, head over to @NASA's Twitter feed or the Artemis blog, where you can listen to an in-depth audio-only conversation about the milestone with guests like Apollo Flight Director Jerry Griffin, Artemis's Najude Moranci, and more. So we're talking about the Apollo 13 record. We know that Apollo 13 traveled, here's that number again, 248,655 miles away from the Earth, and Orion will break that record on November 26th, but Orion isn't going to stop there. It's going to continue on to its maximum distance from the Earth, reaching approximately 272,514.9 miles away from the Earth on November 28th. We won't be live on air for that milestone, but later that day on Monday, we'll be live on NASA TV for a briefing to discuss the midway point of the Artemis mission. And finally, on November 30th, we'll be at the tail end of distant retrograde orbit. We're inserting into that orbit today, and Orion will leave DRO on Wednesday, November 30th to prepare for a splashdown back on Earth. So that was a lot of numbers and dates that I just gave you. We're talking about Orion's distance from the Earth, but also Orion's distance from the lunar surface. It gets a little complicated. So to get a visualization of both of these positions in real time, the Orion program has a great tool online called Arrow, or the Artemis Real-Time Orbit website. We link to it in the Artemis blog, and it's a way for you to see for yourself where the spacecraft is relative to the Earth and the Moon. On your screen now is a look at Arrow. This is what it would look like on your browser. So to recap, we're in a 25.5-day Artemis mission to the moon, and we're in flight day 10. So far in the mission, Artemis performed an outbound powered flyby of the moon and reached its closest approach to the moon, and then it moved further away from the surface of the moon and exited the lunar sphere of influence. Orion has conducted a number of burns to get ready for distant retrograde orbit insertion, and at 3:52 p.m. the burn is expected to begin just less than 15 minutes from now. So today, the milestone for the Orion spacecraft that we're talking about today is the burn to get into a distant retrograde orbit, the distant retrograde orbit insertion burn. So to talk a little bit more about this orbit, let's go to Dan Hewitt at the Moon Board, who can explain a little bit more about what it's all about.
The outbound powered flyby has been complete. We are on our way now to distant retrograde orbit, or DRO. Now we're going to do a maneuver to put ourselves into this orbit and to maintain it. We're going to be about 38,000 miles away from the lunar surface as we orbit around. That's part of why we're calling it distant. And we call it retrograde because the moon orbiting the Earth in this direction, and then we're entering into our orbit in this direction. Opposites, retrograde. Now we're choosing this orbit because it's extremely stable. It doesn't cost a lot of fuel to maintain your position there, and that gives all of our engineers, our flight controllers, the chance to really learn about Orion systems in deep space. Learn about flying a spacecraft farther than we've ever sent one intended for humans. We're going beyond anywhere we ever went for Apollo. And so we're going to be in that orbit, test out all of those systems. Eventually we'll do a maneuver to break out of that, do another flyby and come home. But for now, looking forward to getting into DRO and really getting our chance to learn about Orion on this Artemis I flight. 1 .
So that was a little primer on what this orbit is and why we want to use this mission to meet our test objectives of the Orion spacecraft, but DRO will not be used in future Artemis missions. I'm joined now by Deb Ludbin with NASA's Gateway program. Hey Deb, thanks for joining us.
Thanks so much, Chelsea.
So Deb, Gateway is not going to be in a distant retrograde orbit, is it? What will the lunar outpost be in?
It will not be in a distant retrograde orbit. The Gateway will actually be in a near rectilinear halo orbit, which is a lot of words. We say NRHO, and that is a very different orbit than the DRO. Would you like me to explain a little bit about it?
Yeah, sure.
Okay, so the NRHO, near rectilinear halo orbit, is much more long and skinny, like a long oval. So it actually looks, if you're looking at the moon, more like a necklace hanging down from the moon. It is sort of a combination between two types of orbits that have a lot of things going for it. So the low lunar orbit is more similar to what Apollo did, and that's an orbit that goes sort of around the center of the moon, and it's very close, and it provides great access to the moon. And then the DRO, the distant retrograde orbit, is a much broader, and it usually takes about 2 weeks to get around in an orbit, and it's very circular, and it has great stability, which means you don't need a lot of fuel to stay in orbit, but it also is not very close to the moon. So what we have for the Gateway is we have a near rectilinear halo orbit, NRHO, and that orbit has the benefits of both. So it is both access close to the moon for some of its orbit, where we get to about 90 miles away from the lunar surface, but it also has the stability of a distant retrograde orbit, so that its overall orbit takes about a week, 6.5 days or so, and that orbit offers both the stability of a distant retrograde orbit as well as the access to the lunar surface that a low lunar orbit would have.
Wow, that's really cool. And you're seeing the Gateway that we're talking about now on your screen. And I also see Orion in this graphic. So we heard that Gateway is going to be in this NRHO orbit. Does that mean Orion's going to have to be too?
Sure will. So Orion will do lots of things for Gateway. Orion is the crewed system that will bring crew out to the Gateway so that we can live and work and test out those systems. But at the same time, Orion is going to be bringing some other things out to lunar orbit for us too. So it's very important that the Gateway is in an orbit that both Orion and the human landing system can both access, and Orion will come right up to us.
So we know that Orion's going to need to be in the same orbit as Gateway during future missions, as you just told us. But can you tell us about Orion as a whole? What's its relationship to Gateway, and what's the goal of Gateway, and how does Orion help?
Absolutely. So like I said, Orion is the only way right now that we have to get crew to the Gateway. So that is our number one reason for making sure that we have the staging point of the Gateway small space station in lunar orbit. We can use that as a staging point for Orion to come out and for the human landing system to come out, and everything can meet together there. We can do system checkouts on all of the systems that we will need to go down to the lunar surface, and the Orion crew, which is the Artemis crew at that point, can learn what it's like to live and work farther away from Earth, and learn what it's like to be longer in space, and what happens to people when we're farther away from Earth, when we're significantly farther away from phoning home and calling for help. And so we're using this opportunity with the Gateway to test out all of those systems, both technical and human systems, to make sure that we can work together as an integrated system, which will absolutely be necessary for Mars.
That's right. So we're talking about going to the moon, going to Mars, the Gateway overall. Why is Gateway important part of the Artemis missions?
Gateway is imperative in figuring out how we do a sustainable lunar mission. The Gateway is crew tended. It is not crew habitation all year round. We have crew there for about a month at a time. And for our longer missions, the farther we get away from Earth, the more independent these systems have to be. So we utilize the time on Gateway in learning more about what our systems will do, what our people will do, and it's also a great staging point for future missions. We could actually launch a Mars mission from a system at Gateway, do all of the staging, all the checkouts there, and then have it move on to Mars. And at the same time, we do tons of science. So the good thing about Gateway being there all the time and it being a sustainable system is that we can use that to do science experiments and learn about space weather, learn about radiation, learn about what systems are going to do when they're tended and when they're not tended for significant periods of time. So the Gateway is an imperative imperative position for us enabling sustainable lunar orbit as well as moving forward to Mars.
And that's what it's all about, a sustainable presence on the moon and the science that we can achieve from it. Deb, thank you so much for joining us.
Thank you, Chelsea.
Thanks. We're now coming up on about 6 minutes left until the burn. Shortly before our coverage began today, Flight Director Rick LeBrode conducted a go, no-go poll for the burn, consulting with flight controllers here in the White Flight Control Room, and they all concurred that they are go to proceed with this burn. This distant retrograde insertion burn is expected at 3:52 p.m. Central Time, 4:52 p.m. Eastern. It's going to fire for 1 minute and 28 seconds. Four minutes now until the expected start time of the burn. Now less than 3 minutes away from the burn. You're looking now at an animation of the Orion spacecraft. We intermittently have live views of the Orion spacecraft from its onboard cameras when they're available to us. It's still to be determined whether we'll get live views during this burn or not. And with 1 minute left to go until the burn, it looks like we do have our live views back. "30 seconds away from the expected start of the burn." The burn is nominal so far. Everything proceeding nominally. We're continuing to hear good callouts from flight controllers monitoring the burn. We've reached the end of the burn. The engine has stopped firing. You're getting live views from Mission Control now. We received good callouts of the burn while the burn itself was going on. Flight controllers are just confirming that everything went well. Our coverage today is all about distant retrograde orbit insertion burn, which just commenced minutes ago and concluded about just a little over a minute afterwards. We're back with live views of the spacecraft now. Flight controllers here in the white flight control room looked at all the data from the burn and confirmed that it was a good burn. The burn began as scheduled at 3:52 p.m. Central Time, burning for almost a minute and a half. So it looks like we had a good burn. It began at 3:52 p.m. Central Time, 4:52 p.m. Eastern, burning for 1 minute and 28 seconds. This burn occurred. The start of the burn began about 10 minutes ago. Orion is now traveling at a velocity of 2,252 miles per hour, 57,000 miles above the surface of the moon. And you can follow all of this data in real time using the Arrow Artemis real-time online tracker yourself. We link to this in the blog. We're going to continue to have imagery and videos in high definition from this mission as well as we go on. This is a 25.5-day mission to the moon and back, and we're on flight day 10, having just completed the distant retrograde insertion burn. Many important milestones are expected. We'll be live on air to discuss the midpoint of the mission and for distant retrograde departure as well when the Orion spacecraft departs this distant retrograde orbit that it just entered today. Until then, the next milestone that we have coming up will actually focus on the International Space Station. Live coverage of the SpaceX Commercial Resupply Services 26 mission. It's a cargo mission with the Dragon resupply spacecraft. Begins at 2 p.m. on Saturday, November 26th, with a launch scheduled for 2:20 p.m. Eastern Time. That concludes our coverage for today. This is Mission Control Houston.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Hi, welcome to What's New in Aerospace, sponsored by Boeing. My name is Beth Wilson. I'm a museum educator here at the National Air and Space Museum in Washington, D.C. And today on the program, we are going to be talking about the very first image of a black hole. To begin, I want to introduce our guests from the Phoebe Waterman House Public Observatory, our astronomy educators, Dr. Genevieve de Maizière and Rebecca Lundgren. Thank you all for coming.
Our pleasure.
So last week there was a lot of excitement around the museum because there was a very important confirmation. Tell us what happened last week.
Last week, for the very first time, we now have a picture of a black hole. And why is this special? I mean, black holes are part of our imagination, and people have been theorizing the idea of them for hundreds of years. And we've had really strong evidence for decades that black holes exist. But until now, we have never once actually gotten to see what they really look like to test our theories to see if we were right.
Okay, so let's take a look at this image again, and can you tell us, what are we looking at? It looks like a Krispy Kreme donut.
I definitely went out and got a donut at the end of the day last Wednesday because I was so excited that we had a space donut to look at. Or maybe it looks like maybe a cat's eye or the eye of Sauron. But really what we're seeing here is the black hole's the shadow of its event horizon in the center and hot gas whipping around that black hole at speeds close to the speed of light. And that is bending space-time around it, causing all that stuff that's whipping around it to eventually fall inside the black hole.
Okay, that's kind of complex, I know, but but we've got a demo to demonstrate how a black hole works. So let's get our demo up here. And those of you in the audience, you can watch on these screens. Will be the best place to see this.
All right.
So what are we looking at here?
Yeah. So here we have a piece of fabric. This fabric represents space and time. The fabric of space-time is what we're all in right now, and it's all around us. It's three-dimensional. Here it's 2D though, so we can do the demonstration a little bit better. Now, things that are in space and time generally have mass. That's the stuff that makes us up. We're made out of mass, this floor is made out of mass, everything around us, and things in space.
So here's an example of one thing that has mass, the moon. So anything that has mass is going to interact with the fabric of space-time. So let's see what the impact of something without too much mass has on our model of space-time. See how it's denting space-time just a little bit. It's bending it. Everything with mass bends space, including you. You're bending space just a tiny, tiny, tiny little bit. The moon is bending it, not even enough for us to measure.
However, we're not the biggest things in the universe, no matter how much we want to think we are. There's much bigger things out there, like stars, galaxies made up of stars, and at the center of some galaxies, supermassive black holes. Now, supermassive black holes are small objects that have so much mass and are so dense that they can bend space-time around them in a way that anything that gets close doesn't escape. Let's take a look at what that would look like. So I'm going to take this big object right here that's very massive, and I'm going to put it in space-time, and we're going to see what happens.
Whoa.
What happened to space and time?
It's got a lot heavier.
Yeah.
And it just bent.
Yeah. So you can see that space and time is bending towards this massive object. And if this were in 3 dimensions, we'd see that bending in all directions. So imagine something is traveling near this massive object, like a black hole, like a piece of light. And I'm going to try to send it your way so that you can see it. Let's find out what happens. What happened?
It didn't make it too far.
Can I try it again?
Yeah, sure. Oh.
Almost? Nope.
That was an interesting orbit.
So it still didn't make it anywhere close to you. Because black holes and massive objects like black holes are so heavy, they have so much mass, their gravitational pull can pull everything towards them, even light itself. So from our perspective, it looks like the light gets sucked right into the black hole.
Okay,
Which
so
is
you
why they're
talk
black.
about, go ahead, what?
That's why they're black, because not even light can escape the event horizon of a black hole.
Now you talk about how big this black hole is, right? And the photo that our donut photo that we have, that doesn't look very large.
Well, let's take a look at it. So the photo of that black hole, and I'll take away our demonstration here, that photo of a black hole that we're seeing a small black hole at the center of it called a singularity. That's where all that mass is densely packed. And it's interacting with the space around it, and that space where it starts interacting with things is called the event horizon. So we're seeing the shadow of that event horizon right there in the center. All around it is stuff being pulled towards the black hole because of all that gravity from its mass. It's hot gas that's been ripped off of stars and planets heading towards this black hole, and is spinning, spinning, spinning around it, and it could eventually fall into the black hole itself.
How big is this? What's the size of this? What are we looking at here, this black hole?
Compared to us, it's huge, but compared to things that are out in the universe, not big at all. Take a look at this image. This is an approximate representation of how big this black hole might be compared to our solar system. You can see the sun in the center, Pluto's orbit around the sun, and Voyager, the farthest spacecraft we've ever sent away from Earth, out near the edge. So that means that the center of this black hole, that shadow, is bigger than our entire solar system and farther out than Voyager. But compared to other things in our universe, that's actually pretty small.
That's pretty small? Okay. Our solar system, but it's pretty small. Yeah. All right. Now, I get that the light bends, right? But why does it look fuzzy?
Right. So like Becca was saying, that we're looking at something that's so enormously far away, and on the scale of galaxies, solar systems are really tiny. And so we're trying to see something which is stupendously far away and stupendously small. And in order to see that, even our best efforts are still yielding a fuzzy image. Now, if we were to see it from up close, we would be able to see more detail. But being able to see it at all is an enormous accomplishment that required a global cooperation.
So can we take a look at the spinning? We have a video
Definitely.
here.
So
tell us what's going on here, because this looks sharper
Definitely.
than the image.
If we were to be up close, we might get a little higher resolution or a bigger telescope. So this is a model, a simulation done by scientists on the team of what that kind of would look like, and also from different perspectives. That black hole in the center is so massive that it bends the light around it. So what you're seeing as we change our perspective with the black hole in this video is we see that light being bent around it as well. So we'd be able to see all of those dynamics if we had a little bit better resolution, a little bit, or we were closer, but we can still get all of that information from the image that was taken last week as well.
Okay, so explain to us what the Event Horizon Telescope is, because I understand it's not just one.
Right. So in order to accomplish this incredible feat, in order to be able to see something so incredibly far away and very small, you need a telescope as big as the Earth, which is the Event Horizon Telescope. Now, we don't actually have a single telescope as big as the Earth. That would be really expensive, and it would probably be hard to keep working without breaking under its own weight, for example. So in order to get around that, what the Event Horizon team has done is gather together telescopes all around the world that are acting together. They are simultaneously observing black holes like the one at the center of the galaxy M87, and they're working together to effectively make a single telescope as big as the Earth with holes in it. So that means that they still have some work to do with this data in order to get a good image out of it. But it's basically as big as the Earth.
So Genevieve, I want to ask you, because you spent some time with telescopes in Chile. So were they involved in this program as well? And what can you tell us about the telescopes that you saw when you were there?
Right, so there are multiple telescopes around the world involved in this, in places like Hawaii, the United States, Europe, even Antarctica. And one of those sites was Chile. And the ALMA telescope in Chile is kind of an example of how the Event Horizon Telescope works, but on a smaller scale. Because with ALMA, you have a group of radio antennas on this high, dry, dark location in Chile that act together. When they're looking at an object at the same time, their data is put in the same place and synchronized so that they effectively act as a single larger telescope, which is also on a much bigger scale how the Event Horizon Telescope works.
Now with Event Horizon, all these telescopes we've got working all at once, are they taking photos at different times? I mean, how is this working?
Great question. They definitely need to synchronize. So these telescopes had to be taking a picture of the sky at the exact same time. Now, it wasn't just a little snapshot like you take on your iPhone. This was a long observation done by these telescopes all over the world, but very synchronized at the same time. Then all of that data was collected, and it was so much data that they actually couldn't send it via email to the people they were collaborating with. So they actually had to take big data drives and carry those around physically to be able to then bring the data together to get this picture.
Now I'm going to ask you more about the data in a second, but what I do want to know is, do you guys know how they synchronize those telescopes?
How they synchronize those telescopes? I mean, they're definitely communicating with each other and using the satellites that we have that are globally connected to be able to synchronize their watches exactly and their algorithms and everything that they're using to collect this data.
Even using atomic clocks.
Yes, exactly.
Atomic clocks, okay,
Yeah.
okay.
Yeah.
Now I have some fun facts on this data, and we'll go back to the other photo in a second. This was 5 petabytes of data, which would be a half a ton of hard drives, 5,000 years of MP3 files, and a selfie collection for a lifetime for 40,000 people. Yeah. Do you want to tell us a little bit about this photo and what we're looking at here?
So what we're seeing here is Katie Bowman, a member of the Event Horizon team. She's an electrical engineer and computer scientist. These discoveries take a lot more than just astronomers. You need engineers, you need data scientists, you need educators who can help people understand the results. You need theorists. People from all different branches need to work together in order for us to understand these results. And so what she has here is all of the data from the different telescopes finally brought together in the same place. Funny note, one of the telescopes was in Antarctica, and the observation was taken in April, which is when winter was beginning there. So they couldn't bring all the data together until about 7 months later when the weather was okay in Antarctica to fly it out. So she's got it all together, and she led the team to write the software to start putting this data together so they could start making an image out of it.
Okay, so how do we collect this light? I mean, is there, you said there wasn't just one big telescope. I guess there's a reason for that?
Totally. So there's the reason we're collecting all this data is because we're using radio telescopes. They're collecting the longest wavelength of light, and it's like collecting rainwater. Instead of light, let's imagine it as water in a bucket. So if we had a big bucket, it would cost a lot of money and be hard to fix. That's the bucket that's the size of the Earth, right? We'd love that, but it's really hard. So instead, using these large radio telescopes spread across the world, we can make them like a lot of little buckets collecting rainwater at the same time. They're not going to collect all the rainwater, but by spreading them out, they're going to collect different types of rainwater from different areas and learn different things about the rainwater that's falling, or in this case, the light. Then when you bring all that information together, you can correlate it or layer it on top of each other to get a broader picture of the entire thing that you're looking at. In our analogy, it would be rain, but in this case, it's that radio light that we're looking at in the middle of this galaxy so far away.
Can you tell us a little bit about what radio light is as opposed to like the lights we're sitting under?
So when you hear radio, you think, oh, well, you turn on the car radio and you hear it, right? That's sound. But radio is actually not sound. Radio waves are a form of light. They're just much too red for our eyes to see. Our eyes only see the rainbow of light. But there's light beyond red, which is called infrared, and beyond that is radio. And so these long wavelength forms of light, these low energy kinds of light, are great ways to probe things like what's happening down in the hearts of galaxies, because that light is able to get through all that gas in between us really well.
Okay, so why did we know to look at this galaxy and not another one for this black hole?
So in this case, that's a great question. How would we know to point this giant telescope at this one particular spot on the sky? Now, this is down in the heart of a giant galaxy called M87, an elliptical galaxy with billions of stars in it. But this galaxy has a special trick up its sleeve. What we see here is a Hubble image, but layered onto that Hubble image is a radio image showing a jet. We're going to see a close-up of the part of the galaxy that has the jet shooting out of it here. And so that jet is a narrow, focused beam of particles zipping out of the center of the galaxy, much more focused than a laser pointer and stretching about 5,000 light years in length. Now, what could cause these particles to be moving close to the speed of light, all in the same direction and emitting light as they're going the way that we observe it? The only thing that theorists could think of to explain what we are observing here is a giant black hole with a swirling accretion disk around it, which is powering that jet. So we had a really good indication that there was a supermassive black hole in the center of M87. We didn't have a picture of it, but we had really good evidence of it before the Event Horizon looked at it.
Do you want to tell us what an accretion disk is? And can you point it out on this image and so that we can...
Yeah, if we look at an image of a black hole, an accretion disk can actually occur around any massive object that has stuff spinning around it. In the case of the black hole, the accretion disk that we're seeing is shining with that light because it is hot. It's very, very hot. So much so that it's plasma. It's kind of, some people call it the fourth state of matter. So it's really, really hot, and it's shining bright, and it's swirling around that black hole, spinning around it in a flat disk. So that's why we call it the accretion disk, because it accretes or gathers around it, and then it's spinning around it as well.
How far away is this from us?
The whole galaxy is about 54 million light years away. That means that the light we're getting from it now is 54 million years old.
Is the black hole still there?
Probably, yeah. Probably. On the scale of galaxies, 55 million years isn't a very long time. For example, our solar system has been around for about 4.5 billion years. And our solar, and who knows what was before that and what will come after. So this black hole is probably still there. It might not look the same as this image that we're taking here, but we have pretty good evidence that it's probably still going strong.
Yeah, we have a lot of people in the audience today, and I'm sure they're interested. If they go outside this evening, where would they look in the sky generally to where this galaxy is in this black hole?
So in order to find this galaxy, you'll have to look at the constellation Virgo. And Virgo will rise a little later tonight. So you'll have to wait until well after dark in order to do this tonight. A lot of people can recognize the Big Dipper in the sky. And so look for that pattern of 4 stars in kind of a square and then 3 stars in a curved handle in the sky. That'll be your tool for finding this part of the sky. It's really useful for finding other things too. So that curved handle will arc to the bright star Arcturus and then just keep going and spike down to the bright star Spica, which is in the constellation Virgo. That'll get you in the right part of the sky for seeing this galaxy.
Okay, so black holes for a long time were theory, and part of the theory is time travel. So will black holes allow us to travel through time?
So time and space are inextricably linked. Space-time is one entity in our universe. And what we see when we look at the black hole is we're seeing relativistic effects, which is what you get when things are moving close to the speed of light. And all sorts of weird things that start to happen to both space and time. The way that light is bent around the black hole is very weird and very cool. And it also has effects on time. For example, if you fell into the black hole and I was watching you and you were like shining a light back at me, as you got closer and closer to the black hole, aside from being in a very hot environment with lots of radiation and all sorts of, and being in space and everything, you wouldn't actually notice anything special necessarily as you cross the event horizon. But from my point of view, I would see you move slower and slower, and the light from you would get redder and redder. So it's a kind of a way of time travel when you get close to these very strong gravity fields. But sometimes people also talk about wormholes. Are black holes wormholes? Now, wormholes are kind of a mathematical idea, and they might exist, but we don't know yet. What I can tell when I study the data from the black holes is that they get heavier over time. Like this giant one, this one in the center of M87, it weighs more than 6 billion times as much as the sun. And you make a black hole when you collapse a star, but no star is that big. The only way it got that big was by swallowing other stars, gas clouds, other black holes, things like that, to get bigger over time. That mass is still there in whatever weird, twisted form we don't necessarily understand yet, but it hasn't gone anywhere else.
Becca, what would happen if you put a human through a black hole?
We wouldn't know. We'd never get a signal back. We would probably never ever find out unless they found a way to get out of it or to signal back to us. But of course, we found out that nothing can escape it, even light. And the way we communicate is with light, with radio waves. So we probably wouldn't know anytime soon. So unfortunately, we're probably not going to go into any black holes, but studying them from far can tell us a lot more about their physics and these relativistic effects, which can then help us theorize more of these ideas in the future.
I heard about spaghettification.
Oh, yes.
And so I could be really thin.
Yes, as you fall towards the black hole, from our perspective, it'll look like you've strung out into like literally your atoms, the smallest particle of you, and it'll look like you're a long line of spaghetti. So that is an actual scientific word, spaghettification.
That will be a word I remember. Why is this image so important?
So to me, a big part of why it's so important is, like, look at everyone who's here. We think black holes are cool. Black holes really resonate with people. They're such a weird and marvelous phenomenon that people just like them. And so getting to see an actual picture of one for the first time ever is, I think, just by itself, really cool. I think everyone can kind of appreciate that. But it can also help us test our theories. So we have all these theories and simulations and artists' conceptions of what a black hole would look like, what's happening inside it, how does Einstein's relativity interact with, say, gravity and interact with quantum mechanics. But the